February 27th, 2026, a control room at NASA's Jet Propulsion Laboratory. Engineers are watching a screen that should be showing routine numbers. Instead, the power readings from a spacecraft 15 billion miles away are doing something they weren't supposed to do. They're dropping, not by a lot. Not enough to trigger an alarm bell in a movie, but enough to make a room full of some of the most experienced spacecraft engineers on the planet go very, very quiet, because they know exactly what that drop could mean. And they know that whatever decision they make next, they won't find out if it worked for almost 2 full days. The spacecraft is Voyager 1. It is 48 years old. It was built before most of the engineers currently keeping it alive were born. And what NASA discovered in its data this year is forcing scientists to rethink something they thought they understood. What actually exists in the space beyond our solar system. This is not a routine update. This is the story of a machine that was supposed to die decades ago, still sending back secrets from a region of the universe no human instrument has ever touched. At the exact moment, its power is running out. Let's start with where Voyager 1 actually is right now, because the number alone is almost impossible to hold in your head. Voyager 1 is more than 25 billion kilometers from Earth. To put that in perspective, light, the fastest thing that exists, the thing that crosses the 150 million kilometers between the Sun and Earth in about 8 minutes, takes nearly a full day to reach Voyager 1. Not minutes, not hours, a full day. In November 2026, Voyager 1 is set to become the first human-made object in history to cross that threshold. 1 full light day from home. No spacecraft, no probe, nothing built by human hands has ever been that far away and still been talking to us. And it is still talking. That's the part that keeps surprising even the people who work on this mission every day. A machine built in the 1970s, using less processing power than a modern calculator, running on a power source that was only ever expected to last a few decades, is still transmitting data from a region of space that didn't even have a name when it launched. To understand what's happening now, you need to understand what Voyager 1 already proved once before. In August 2012, after 35 years of travel, Voyager 1 crossed a boundary called the heliopause, the edge of the heliosphere, the enormous bubble of charged particles blown outward by our sun that surrounds the entire solar system like an invisible shield. Everything we've ever explored directly, every planet, every moon, every mission, has existed inside that bubble. Beyond it is something else, interstellar space, the actual gap between star systems. Voyager 1 became the first human object to leave that shield and enter it. For years, scientists assumed that once you crossed that line, you'd find something close to empty, uniform nothingness, a void, a vacuum in the truest sense. That's what the models predicted. That is not what Voyager 1 found. Since 2017, Voyager 1's plasma wave instrument, one of the few pieces of hardware still functioning on the spacecraft, has been picking up something scientists did not expect. Persistent, structured wave activity in the plasma surrounding the spacecraft. Not silence, not static. A signal. A kind of steady vibration in the density of the material between the stars, one that reveals large-scale structure and turbulence that pre-crossing models simply did not predict. Interstellar space, it turns out, is not calm. It has texture. It has motion. Regions of it behave less like an empty room and more like an ocean with slow, deep currents running through it. Currents on a scale that dwarfs entire planetary systems. That alone rewrote a chapter of astrophysics textbooks. But it's what happened starting in 2020 that has scientists at JPL and beyond talking in a very different tone. Voyager 1's instruments began detecting something in the magnetic field and plasma density around the spacecraft that didn't match any existing model. Not a small deviation. A sustained, elevated reading, stronger magnetic intensity, denser plasma, that the spacecraft has now been moving through for years, not days. And the leading explanation some mission scientists have proposed is almost hard to say out loud without pausing. Voyager 1 may have entered a small ancient cloud of interstellar material, a relic carrying the magnetic signature of a star that died, or a star-forming region that erupted, potentially millions of years ago. Sit with that for a second. Our entire solar system, all 8 planets, the asteroid belt, everything we've ever called home, may currently be drifting through or near the leftover debris of something that happened in this part of the galaxy long before humans existed. A ghost signature embedded in the fabric of space that our own protective bubble is now pushing up against. If that holds up under further analysis, it means the boundary between our solar system and the rest of the galaxy isn't a fixed, static line the way we've always pictured it. It's active. It shifts depending on what ancient material we happen to be passing through at any given moment in our slow multi-million-year orbit around the galactic center. The environment protecting Earth from the harsher radiation of deep space might not be constant. It might be something that changes as we move, something our solar system has been quietly plowing through, oblivious, for longer than we've had the instruments to notice. And the only reason we know any of this The only reason humanity has this data at all is because one aging, half-crippled spacecraft happened to be in exactly the right place to measure it. But here's the part of the story that makes this discovery feel more urgent than almost any other finding in the mission's history. Voyager 1 is dying while it tells us this. Both Voyager probes run on something called a radioisotope thermoelectric generator, essentially a nuclear battery that converts the heat from decaying plutonium into electricity. There's no sunlight to draw from this far out. Solar panels would be useless. And that power source loses roughly 4 watts every single year. It doesn't sound dramatic until you realize that after nearly 5 decades, there is almost nothing left to spare. Every watt is now being fought over by systems competing to keep the spacecraft's instruments alive. Its internal temperature above freezing, and its antenna pointed at a planet 25 billion kilometers away. On April 17th, 2026, engineers made a decision that had been building for months. They sent a command, one that would take nearly a full day just to arrive, instructing Voyager 1 to permanently shut down one of its instruments, the Low-Energy Charged Particles Experiment. This instrument had been running almost continuously since launch in 1977, 49 years without a real break. It was one of the tools that had helped confirm exactly when Voyager crossed into interstellar space in the first place. And on that day, it went silent. For good, unless something changes. Of the 10 original science instruments Voyager 1 carried into space, 7 have now been switched off, one by one over the decades. Each shut down a small, deliberate act of triage to keep the spacecraft breathing a little longer. With this latest one gone, only 2 remain. An instrument that measures the magnetic field and the plasma wave detector. The very instrument responsible for finding that mysterious ancient cloud in the first place. Why now? The trigger was a routine maneuver in late February 2026, a scheduled role to keep the antenna aligned with Earth. During that maneuver, power levels dipped unexpectedly. Not catastrophically, but enough that engineers realized any further drop could trip the spacecraft's automatic undervoltage protection system, a failsafe that would start shutting things down on its own, with far less control and far more risk than a deliberate, planned shutdown. So the team made the call themselves on their own terms, rather than risk the spacecraft doing it for them in some unpredictable configuration, nearly a full day's communication delay away. This is what the mission has quietly become. Not exploration in the traditional sense, but survival management. A team of engineers performing what amounts to slow, careful triage on a patient lying on an operating table 25 billion kilometers away, where every single decision, every command sent, every response received, takes almost 2 full days round trip to confirm. And it isn't just power. Some of Voyager 1's thrusters, the ones responsible for keeping its antenna pointed precisely at Earth, have partially clogged fuel lines, a slow mechanical problem with no fix available from this distance. There is no backup thruster system left. In the words of Voyager's own project manager, everything on the spacecraft at this point is single string. Engineering language for exactly what it sounds like. No redundancy, no safety net. If the one remaining thruster system fails, the antenna could begin to drift and the signal, a whisper of data traveling at just 160 bits per second, slower than a dial-up modem from the 1990s, could go quiet permanently. Even communicating with Voyager 1 at all depends on a narrow, fragile setup. Between May 2025 and February 2026, the primary antenna complex capable of sending commands to both Voyager spacecraft, a facility in Canberra, Australia, was offline for major upgrades, with only a couple of brief operational windows available. For months, engineers could receive Voyager's data, but they couldn't send it any new instructions at all. They could listen, they couldn't speak. The moment that antenna came back online earlier this year, the very first major action the team took was the decision to shut down that instrument, a call they'd already been planning and waiting on for months. But NASA hasn't given up. Far from it. Engineers are now preparing something they've internally nicknamed the Big Bang, a high-risk, high-reward maneuver where a whole cluster of powered systems get swapped out essentially all at once, trading some components for lower-power alternatives to squeeze out more time and more science before the lights go out for good. It's being tested first on Voyager 2, which has slightly more power margin and is somewhat closer to home, making it the safer place to try it. If it works there, the same procedure will be attempted on Voyager 1 sometime after mid-2026. And if it succeeds, there is a real possibility that the instrument just shut down in April could be switched back on. The eye that just closed could reopen. Matt Hill, the scientist who has led that instrument's research for years, put it simply, that data helped reveal the properties of cosmic rays and solar particles, and helped pinpoint the very moment Voyager crossed out of our solar system. He said the team is holding on to hope that engineers can bring it back to life so they can keep learning whatever else is waiting out there. That single word, surprises, is carrying a lot of weight. Because interstellar space has already surprised everyone once. And it doesn't sound like it's finished. Let's talk about what those two surviving instruments are actually picking up, because this is where the story stops being about engineering and starts being about genuine discovery. The magnetometer is doing something no Earth-based observatory could ever do. It's measuring the structure of the galactic magnetic field directly from inside it. That field is one of the least understood forces shaping our galaxy. Scientists believe it plays a role in steering cosmic rays, in regulating how new stars are born, and shaping the long, slow evolution of the Milky Way itself over billions of years. And right now, at this exact moment, there's a single point of direct measurement out there, moving through that field as our solar system carries it along. The plasma wave instrument, meanwhile, has picked up something scientists nicknamed the hum of interstellar space, a faint, steady, persistent tone in the data, distinct from the sharper spikes triggered by solar storms. It's not caused by any single event. It's just there in the background all the time, a kind of baseline vibration running through the plasma that fills the space between star systems. Researchers believe this hum means they can track the density of interstellar material continuously, even during the quiet stretches when no solar shockwave is rippling outward to trigger a dramatic reading. In other words, interstellar space has its own steady heartbeat, and for the first time in history, we have an instrument close enough to actually hear it. There's another layer to this that makes the discovery even stranger. Our solar system doesn't sit in some generic, average patch of the galaxy. It sits inside what astronomers call the local bubble, a vast cavity roughly 1,000 light-years across, carved out by a series of ancient supernova explosions that went off in this region 10 to 20 million years ago. The material inside that bubble is thinner, hotter, and structured very differently than typical interstellar space. And the boundaries within that bubble aren't smooth. They're layered, uneven, shaped by overlapping shock waves from stars that died long before humans existed to notice. Voyager 1 is sampling one exact point along one exact trajectory at one specific moment in our solar system's multi-hundred-million-year journey around the galactic core. And even at that single point, it's finding structure nobody expected. A reminder that everything we assumed about the smooth, empty space between stars was built from models and remote observations, made entirely from the safety of inside our own protective bubble. It's worth remembering what this spacecraft was actually built to do, because the gap between its original mission and what it's accomplishing now is almost staggering. Voyager 1 launched on September 5th, 1977, riding a Titan rocket out of Cape Canaveral. Its job, on paper, was simple. Fly past Jupiter, fly past Saturn, take pictures, measure some magnetic fields, and call it done. 5 years, 2 planets, mission complete. In 1990, once that primary mission was long finished and the spacecraft was already leaving the solar system behind, engineers turned its camera around one last time and captured a photograph that would become one of the most famous images ever taken. Earth, reduced to a single pale point of light suspended in a sunbeam, photographed from nearly 6 billion kilometers away. Carl Sagan, who helped push for that photo to be taken, described it as a mote of dust, a reminder of just how small and fragile our entire world really is against the scale of everything else. Then the cameras were switched off for good, to save power for instruments that could keep collecting data long after there was nothing left to photograph. That's the spacecraft that, 36 years later, is now telling us that the region beyond our solar system isn't the quiet void we assumed it was, but something layered with ancient history, still shaped by explosions that happened before our sun's light had ever reached this corner of the galaxy. Even with everything running perfectly, the math is not forgiving. Voyager 1's power source may only supply enough electricity to keep sending basic engineering data until sometime around the mid-2030s. Engineers estimate the recent shutdown alone buys the mission roughly 1 more year of breathing room. Just enough, they hope, to reach the 50th anniversary of launch in 2027. Half a century. A machine designed to survive 5 years, reaching for 50, still transmitting from a distance so vast that the light carrying its signal takes nearly a full day to get here. Every command sent to Voyager 1 now has to travel through a communication delay that's almost impossible to make peace with. Light itself, moving at its absolute maximum speed, takes close to a full day to cross the distance separating Earth from the spacecraft. That means when engineers send an instruction, even something as small as asking the spacecraft to confirm a status reading, they don't get an answer for nearly 2 days. Send the command, wait almost 24 hours for it to arrive, wait almost 24 hours more for the response to come back. If anything about that response is unexpected, if there's the smallest ambiguity or error, the whole cycle starts over. 2 more days just to check. This isn't engineering in any conventional sense anymore. It's closer to slow, careful archaeology, carefully excavating a fragile signal from across the solar system, one agonizingly patient exchange at a time, knowing that a single mistake could cost weeks. And there's no backup plan waiting in the wings. There's no Voyager 3 on a launch pad ready to take over. Other missions exploring the outer solar system are either headed in different directions entirely or won't reach the same boundary for decades. A dedicated successor mission has been discussed for years, but remains, as of now, only a concept, nowhere close to funded or built. Which means that when Voyager 1 finally goes silent, whenever that day comes, there will be a real, measurable gap. A window where humanity has no direct instrument sampling the space beyond our sun's influence at all, just the data Voyager 1 managed to send back before it stopped. So what does all of this actually mean for us, here, on this small planet tucked deep inside the solar system's protective bubble? It means some of our most basic assumptions about our place in the galaxy need a second look. We used to think of the edge of the solar system as a clean, simple line. Cross it, and you're in the calm emptiness of deep space. Voyager 1 has shown us that's not true. The boundary is turbulent, it's alive with structure, and the region just beyond it may be shaped by the leftover debris of ancient stellar events. Material that could be influencing how much protection our heliosphere actually provides against the harsher radiation of the galaxy at large. Radiation that, over very long timescales, can influence things like atmospheric chemistry back here on Earth. It means the protective shield around our entire solar system might not be a constant. It might be something that flexes and changes as we drift through different regions of space over millions of years, something that was thought to be fixed and turns out to be dynamic. And it means that everything we're learning right now is coming from a single, tiny, failing spacecraft built by engineers in the 1970s who thought they were sending something to photograph Jupiter's clouds and Saturn's rings. They had no idea they were building humanity's only direct witness to the space between the stars. They gave it 5 years. It gave us 49 and counting. Voyager 1 also carries something beyond its scientific instruments. A golden record, etched with sounds and images of Earth, greetings in dozens of languages, music spanning genres and continents. A message, sealed and sent outward in case anything out there ever finds it. Whatever happens to the instruments still running, whatever happens to the last flickering watt of power keeping this spacecraft alive, that record will keep drifting outward. Long after Voyager 1 stops talking to us, it will still be carrying a piece of who we were, moving silently through the same strange, structured darkness it just spent years teaching us how to understand. Right now, in 2026, none of that has happened yet. The mission isn't over. The signal, faint as it is still arriving, one slow 160 bit per second whisper at a time, carrying information that no other machine in human history has ever been positioned to collect. 2 instruments are still working. Engineers are still fighting for every extra watt, every extra month, every extra year they can find. And somewhere out there, 25 billion kilometers away, and getting farther by the second, a machine older than most of the people tracking it is still measuring the magnetic hum of interstellar space, still recording the aftershocks of solar storms rippling outward for years across the void, still quietly rewriting what we thought we knew about the space beyond our home. It doesn't know any of this is historic. It's just doing what it was built to do, decades past its expiration date, sending back everything it has left before the dark finally catches up with it. If this kind of story pulls you in, real science, real stakes, happening right now, farther from home than anything human-made has ever gone, subscribe, because there's a lot more of this universe left to explore, and we're just getting started.